Good morning, good afternoon, and good evening to all of our viewers from around the world. Welcome to the fourth talk in the inaugural webinar series presented by the International Adsorption Society. The IAS is an international organization dedicated to advancing adsorption as a solution to scientific, engineering, and human welfare challenges through the promotion of adsorption research and education. We hope that all of our attendees, their families, and their colleagues are safe amid the ongoing COVID-19 pandemic. Today's webinar will be presented by Professor Randy Snurr of Northwestern University. I'm Daniel Siderius of NIST in the United States and the Secretary-Treasurer of the IAS. Questions to our speaker will be moderated by Professor Arvind Rajendran and Nick Wilkins, both of the University of Alberta. We are required to remind attendees and future viewers that the views expressed by the speaker, host, or other moderators are not necessarily those of the IAS or the institutions associated with those individuals. We ask that you consider joining the IAS as a regular member if you are not already. Our dues are minimal, only $20 US per year, but support the publication of our flagship journal, Adsorption, contribute to travel grants and workshop seed funding for IAS members and affiliated groups, as well as aid the organization of our triennial conference on the fundamentals of adsorption. Members also receive free access to IAS-supported materials, including our journal, as well as the adsorption database published by Springer Materials. We've already seen a noticeable uptick in membership as a result of these webinars, and we hope that this new way of engaging our membership and affiliated persons will continue to improve our society overall. Anyone can follow the IAS Twitter at @IntAdSoc for future updates regarding IAS events, webinars, and information about scientific meetings. Please help expand our YouTube channel by subscribing. During the webinar today, questions can be submitted to the speaker via the Q&A tab of the Zoom client or as comments on YouTube, and those comments will be forwarded to the Zoom hosts. We will pause for questions about halfway through the webinar and then take additional questions at the end. And now I'm very pleased to introduce today's speaker, Professor Randy Snurr of Northwestern University.
Good morning. I'd like to thank Dan Siderius and Arvind Rajendran and the International Adsorption Society for putting together this series of webinars. So this morning, I'm going to talk about using molecular simulation to predict properties of adsorption systems. So you might ask, well, why would we want to use molecular modeling? And there are a number of potential reasons. Sometimes experiments are difficult. We might be interested in something under very high pressure or very high temperature that might be difficult to do experimentally, but that we might be able to access easily with modeling. Modeling can sometimes provide information that's difficult to obtain from experiments. If we're modeling a system at the molecular level, we can actually see where all of the atoms are, and that may be difficult to do in experiment. If a single model provides us with information from a whole variety of different experiments, that can be useful. It provides a single coherent picture. Sometimes, for example, in adsorption systems, the macroscopic properties are very sensitive to molecular level details, and so we want to do modeling at the molecular level. And sometimes simplified models can shed light on very complicated systems. And I want to stress throughout the talk that modeling and experiment are best used together. Now, what I talked about on this slide, these are very general statements that would be true for modeling any material system. What about adsorption specifically? Well, an obvious place to start would be we might want to be able to predict adsorption isotherms for single component systems. From those same simulations, we can get the enthalpy of adsorption. And isotherms are something that you can measure very easily, and maybe it's easier to do the experiment. Adsorption enthalpies are a little harder to get from experiment, and mixtures are sometimes very difficult to get from experiment, but we can easily do them with simulation. And as I mentioned before, we can get detailed information on where the molecules sit in the pores. So in the example shown here, you can see the green molecules seem to like these horizontal channels, and the blue molecules prefer the vertical channels. And we might try to understand what implication that has for, say, separation. But again, I encourage you to think about the idea that we want to use modeling together with experiment. So the objectives for the next 45 minutes or so are to provide a brief introduction to molecular simulation of adsorption. So we'll talk about how to develop or put together a model, a so-called force field model. And then we'll talk about how do you predict properties from the model using Monte Carlo simulations. And I'll try to illustrate these methods with some examples as we go along. So this slide is the one slide overview of the whole talk. So this is our plan. We'd like to predict, say, an adsorption isotherm. So the isotherm tells us about the molecules inside the pore. So we'll start by specifying the temperature and pressure and the composition of the fluid outside of the pore. That'll be an input to our simulation. And then we'll need a model. We'll need models for the fluid and the solid. So if we're modeling CO2, for example, we might model it in atomistic detail, including the carbon and the two oxygens. If we're simulating a MOF, we might have the crystal structure and know where all of these atoms are sitting. And so those would be inputs to the simulation. We also need then equations that tell us about the energetic interactions between the atoms. And we will refer to that as a force field. All of those things will then be fed into large-scale computer simulations based on statistical mechanics. And the main tool that we'll talk about today is Grand Canonical Monte Carlo simulation, or GCMC. And from those simulations, we can then predict adsorption isotherms, we can get enthalpies of adsorption, we can look at selectivities if we're simulating a mixture, and we get detailed information on how the molecules sit in the pores and interact with the pore walls and with each other. So I said these simulations are based on statistical mechanics, and that's a very rich field. Many of you may have taken a class or even two classes in that field, but here's the main goal of statistical mechanics. We'd like to be able to connect the molecular level picture of a system with the macroscopic thermodynamic and transport properties. That's our objective. And if you think about a glass of water, there are just a handful of macroscopic properties that describe that glass of water. We could specify the temperature, the pressure, the density. We might then also measure the heat capacity, transport properties like viscosity or the diffusion coefficient. But there are a finite number, a small number of such variables. If we zoom into the molecular level, what are the variables? Well, they're the positions and velocities of roughly 10 to the 23rd particles. So we have 10 to the 23rd variables. And the goal of statistical mechanics is to relate that molecular picture with the macroscopic picture. And the word statistical comes in because for this handful of macroscopic variables, there are many different arrangements of the molecules that are consistent with that macroscopic picture. And so at the molecular level, we will average over or obtain statistics on those molecular configurations and use that to calculate the macroscopic properties. Okay, so we need a model. First of all, I want to say the models that we're talking about today are based on classical, not quantum mechanics. And we'll often refer to this as a force field. And these are sometimes called molecular mechanics, in contrast to quantum mechanics. So we're going to need to specify the functional form of the equations and the parameters. And the idea is we're going to write expressions for the energy of the system and obtain that energy by adding up different contributions like the ones listed here. So we'll have contributions from bond stretching. A bond will have a particular equilibrium length where the energy is lowest. But if you stretch the bond, the energy goes up, or if you compress the bond, the energy goes up. So we want to capture that. Similar considerations for bond angle bending. Torsion angles will have preferred, say, Gaussian trans configurations. And then we'll also have terms that tell us about non-bonded interactions, say the interactions between two argon atoms that are not, obviously not bonded to one another. So this would be a typical form for a force field. The particular force field here is referred to as driding. This is from the literature. So here the total energy has the different terms that are listed here. So for example, the bond stretching is represented by a harmonic potential. Similarly, for the bond angle bending, torsion potentials are often written as cosine expansions. And then for the non-bonded interactions, the dispersion and repulsion interactions, a typical form would be this common Lennard-Jones potential. So the expression shown here. And then often, we also think about there being partial charges on the atoms, and we would represent those interactions with just normal Coulomb's law. So we have the form of the equations, which could vary in different force fields. And then we have all of these parameters. For example, we need to know K and R naught for different types of bonds. So where do you get all of these parameters? Well, one option is other people have developed one and you can use it. So if you're going to do that, you should keep in mind that different force fields have different targets. For example, if you're interested in biological systems, there are things like amber and charm. Those force fields are developed specifically for biological systems. More generally, if we think about vapor-liquid equilibrium, the trap potentials from Ilya Zietman's group, I put those in blue because we often use those in adsorption systems to represent guest-guest interactions, or to represent a gas phase or a liquid phase. So those are developed specifically to reproduce thermodynamic properties and in particular vapor-liquid equilibrium. And then there are a few very generic force fields. I mentioned driding, UFF is another one. These were meant to be generic force fields for a major portion of the periodic table, but not developed specifically for any particular system. And then for some systems, there are specialized force fields that have been developed. So in the adsorption area, there's specialized force fields that several groups have developed for zeolites, for example. So if you're going to simulate zeolites, those might be a really good place to start. So each of these force fields contains a large number of parameters and equations, like we looked at on the previous slide. If you're using commercial software, many of these force fields are already in those software packages. That's also true of some academic packages. And the results are generally more sensitive to the torsion and especially the non-bonded parameters. Those are the ones that really affect the results. And finally, I'll point out that parameterization is difficult. And if you change one parameter, it can affect the others. So you really should think of the force field as a single entity. You don't want to take, say, the Lennard-Jones parameter for oxygen from one force field and other parameters from another force field and just put them together. You want to try to avoid that if you can. So these will be established force fields. Or you might try to fit your own. Maybe you're forced to. So if you're doing that, things to think about: bond stretch, bond bending, torsion parameters. Those often come from spectroscopy or quantum mechanical calculations. Those are often well known. The Coulomb interactions can also be obtained by doing quantum mechanical calculations to calculate partial charges for atoms. So for example, if you're looking at a CO molecule, you would want to reflect the dipole moment of the molecule. The dispersion interactions, the van der Waals interactions, those are difficult to calculate from quantum mechanical calculations, and those may be fit empirically to match some experimental data you have in a training set. for adsorption, for example, maybe you try to fit the adsorption isotherm. And then in developing a force field, you'd like it to be transferable from one system to another. So for example, if you have parameters for sp3 carbon atoms, those would typically be good for any molecule that has that sort of atom. So you would use the same parameters in propane and hexane and octane for the carbon atoms. And I'll just say that this is not an easy task, but these are at least a few things to think about or to understand that go into these force fields. So how many atoms can you simulate? Well, 1,000, 10,000 maybe. 1,000,000 would be a big simulation, would require a lot of computer time. But even 1,000,000 atoms is a lot less than 10 to the 23rd atoms. So if you're simulating a small number of atoms, as shown here, a lot of them are on the edge of the system. And if your system is surrounded by vacuum or a wall, well, that's very different than a bulk fluid, and may not be representative of what you really want to simulate. So what people typically do to get around this problem is they use what are known as periodic boundary conditions. These atoms in our simulation box, we're keeping track of those, we're simulating them, but we surround this box by periodic images of the central box. And what this means is that if an atom in the central box, say this one, if this one leaves on this side, its image comes into the box on the other side over here. And if you play video games, this is a common strategy in certain, at least older video games. Okay, so let's look at an example. A number of years ago, my group wanted to simulate carbon dioxide in metal organic frameworks, or MOFs. So MOFs are crystalline, so that's a big advantage for doing these simulations. So we decided to use an atomistic representation of the MOF. We found the crystal structures in the literature, and we placed all of these atoms at their crystallographic coordinates. And in that work, we kept all of these atoms fixed at those coordinates. On each of these framework atoms, then we placed the Lennard-Jones site. So we used those Lennard-Jones potentials. And this was pretty new in the MOF field. Other people hadn't simulated them very much. We weren't sure what parameters to use. So we just used these very generic Dryden parameters and decided to see if it worked. For CO2, we used, as I mentioned, these trap force fields from the group of Ilya Siepman. And so we used those for the interactions between CO2 molecules with each other. And those are, again, a fairly simple Lennard-Jones plus Coulomb potential. So we have a Lennard-Jones site and a partial charge on each of these CO2 atoms. So this is a pretty simple force field. This is the MOF we started with, MOF1, also known as MOF5. It has these pores of about 11 and 14 angstroms. And so we tried it out. So this was work done by Krista Walton and David Dubaldam when they were in my group. And we had some experimental data from the group of Omar Yagi. His student, Andrew Millward, had measured these very interesting isotherms for CO2, these strange steps. And with this simple model, we were able to reproduce these steps and understand a little bit about why they occur. And we could do this not just in MOF1, but we also looked at a few other MOFs. And again, the agreement's not perfect, but given the simplicity of the model, it's pretty good. And I want to stress that, this is really a prediction. We're not fitting the model to match this data. And then in other work in the group over the years, we've looked at other species. So this is methane. Again, we used the trap force field with Dryden for the framework. And again, it matches the experiments quite well. Hydrogen, a similar story. And I'm not going to talk much about diffusion today, but I just wanted to point out with the same type of model, we were also able to simulate the diffusion coefficients of linear alkanes in this same MOF, MOF1, in very good agreement with pulse field gradient NMR experimental data. Okay, so we've talked about putting together a model. Now we need to talk about what do we do with the model? How do we actually calculate those isotherms that I showed you in the previous slides? I'll take a quick detour just for 2 slides and talk about molecular dynamics simulations. So these will be used to calculate diffusion, for example, and they're pretty simple to understand, so I thought it was a good place to start. So the idea with an MD simulation is we want to simulate the evolution of the system in time and calculate structural, thermodynamic, transport, and dynamic properties. And the idea is simple. We will just integrate Newton's equations of motion numerically. So F equals ma. So what does that mean? Well, for every particle I, we can calculate the force at a given configuration of the system. How do we do that? Well, we can get it from the force field. The force field gives us the energy, which here I'm indicating with this V, and the force is just the negative gradient of the potential energy. So for a given configuration, we can get the force that each atom feels, and that then gives us the acceleration, and we can think about marching along in time. So if we have the positions and velocities and the acceleration from the force of an atom at a given time, we can use something like the velocity Verlet algorithm to predict the position at t plus delta t, some small time step in the future. Similarly, we can get then the new velocities. And so now we just do this for all of the atoms and move them forward this small time step, and then we repeat. Again, recalculate the forces, get the accelerations, and just keep repeating this. And basically, it gives you a sort of movie of the system. The atoms move according to the forces that they feel from things like bond stretching, from bouncing into other atoms, and so on, all of the things that we put into our force field. So in MD, we move the particles deterministically from the Newtonian equations of motion. Our main topic today, though, is Monte Carlo. So in Monte Carlo, we're going to move the particles stochastically. We're going to generate configurations randomly and accept or reject them according to the Boltzmann probability, which is one of the main ideas from statistical mechanics. So this Boltzmann weight tells us that low energies are preferred, higher energies are sometimes visited, but they're less likely. And this parameter beta is 1 over kT, where T is the temperature and K is Boltzmann's constant. So this is a key concept that we'll take from statistical mechanics. So let's start with just something simple. Let's think about doing Monte Carlo simulation of liquid argon with a fixed number of molecules N, fixed volume V, and fixed temperature T. So if you're familiar with statistical mechanics, that would be the canonical ensemble, fixed N, V, and T. Argon is simple. We might just have Lennard-Jones parameter or Lennard-Jones sites on all of the atoms. The total energy would be obtained by adding up all of those pairwise interactions between all of the Lennard-Jones sites in the system. So how do we simulate it? Well, we'll make random moves of the particles, and we will accept or reject them according to this Boltzmann weight. And let's just jump to the next slide and see this. So we have a configuration M. We want to generate the new configuration. So we'll randomly select one of the particles that has this current position, and we will attempt to displace that particle a small distance from its current position. We'll calculate the new trial position for that molecule I, and then we'll calculate what would the change in energy be if we were to move the particle. So we'll use our force field to get that. If the new energy is lower than the old energy, you accept the move automatically, and you jump down here. If the new energy is higher, then you calculate this Boltzmann weight, which would depend on the temperature, and then you generate a random number between 0 and 1, and then you check, is this Boltzmann weight larger than the random number? If it is, you accept the move. If it's not, then you reject the move, and you keep the old configuration. You enter it you keep the old configuration and put it into the average again. And sometimes that seems wrong, but that is the correct way to do this. So now you have the new state, and then you enter that into your averages, and then you check, well, have I done enough configurations? If you have, you're done. Otherwise, you go back and you repeat this millions of times and calculate millions of configurations of your system, and then you average over them to calculate things like, say, the average potential energy, or look at where the molecules are sitting. So that last question on the slide, how do you know when you're done? In general, this is not an easy question to answer, but the best practice is to just plot some property of interest versus the number of Monte Carlo steps and look to see if it's flattened out. So in the example shown here, you can see we're starting with this property down here, and it goes up and up and up, and then it plateaus. And so here the system is equilibrating, and we don't want to include that in our averages. We would start averaging here at the red line and average over these configurations. And these fluctuations, those are real. We want to see that, but they're fluctuating around some average value that has stabilized. So in this case, it's pretty obvious that you can see, yeah, it's equilibrated. You can see when it has equilibrated. Sometimes it's less obvious. This is sort of drifting up and down. It's hard to tell. So there's a little bit of an art to answering this question, but it's certainly something that you want to be aware of. Okay, so how do we actually get an isotherm? I talked about doing a simulation at constant N, V, and T, but how do you get an isotherm? And maybe this is a good spot to stop and see if there are any questions before I go on with that.
So I have one question here from Philip for Malik. How do you usually calculate partial charges for MOFs?
There are a number of different methods for doing this. The methods we like best are ones based on quantum mechanical calculations that try to reproduce the electrostatic field around the species by basically fitting the charges to reproduce that electrostatic field that you would get from the quantum mechanical calculation. And that could either be done on small pieces of the MOF or for a full periodic system.
And I have a quick question. When you make these moves, do you expect to have anything like a local minima that they could get trapped into?
Yes, it is something to worry about. Yeah, if you're making just local moves, you could imagine if there's a very large barrier between one minimum and another, if you're only making local moves, it might be difficult to get over that barrier. And so in cases like that, you can think about making more aggressive moves rather than just small variations of the system. You can make bigger variations, and sometimes there are biased Monte Carlo methods that allow you to, that are basically designed for overcoming those sorts of barriers.
Thanks, Randy. I think we are done with questions for the moment. We can proceed.
Okay, so we'll keep going. Yeah, so in adsorption, one of the main things we would want to calculate is an adsorption isotherm. So let's step back and think about, what are we looking at here? Adsorption is a phase equilibrium problem, right? We have some adsorbed phase in contact with a fluid phase. We're assuming that they are in equilibrium. We know, say, the temperature and pressure and composition out here. We want to calculate what goes inside. So one way you might think about doing this would be, well, you could simulate both phases, maybe in direct contact, and there's some problems with doing that, so people don't really do that. Or you could simulate the two phases kind of separately, and that's a method called Gibbs Monte Carlo, which I decided to skip today. But instead, what people often do is we will invoke some thermodynamics. We'll think back to, well, what is true if these two phases are in equilibrium with each other? We know from thermodynamics that if the two phases are in equilibrium, they have to have the same temperature, the same pressure, And for each species I, the chemical potential has to be the same in the two phases. And if you don't like chemical potential, you could use the fugacity instead. So what we're going to do is we will just simulate the adsorbed phase. And to establish the equilibrium with the fluid phase, we will set the chemical potential. And that will make this connection with the other phase. So we will do the simulations with fixed chemical potential, volume, and temperature. So from statistical mechanics, this means that we're in the grand canonical ensemble. So these are referred to as grand canonical Monte Carlo simulations, or GCMC. And if you work in the adsorption area, you see this quite commonly, that people are doing GCMC simulations. So the idea is we have this adsorbed phase in equilibrium with a bulk fluid, but we're not going to simulate the bulk fluid. We will represent it purely through its chemical potential and the temperature. Now, what this means is if the chemical potential is fixed, the conjugate variable from thermodynamics, which would be the number of molecules, that will fluctuate. So the moves that we will use in our Monte Carlo simulation will have translations and rotations of molecules, just like in the simple NVT case. But we will also need moves that change the number of particles in the system. So we'll have moves where we insert new molecules into the system, or moves where we take an existing molecule and remove it from the system. So a little detail here how would this work. So translations, you would pick a random molecule, perturb its position, as we talked about before, calculate the change in energy, and accept or reject the move based on this Boltzmann weight, just like we saw before. What about an insertion? So for an insertion, we'll pick a random spot in our simulation box, attempt to put a new molecule there, and calculate the change in energy, and accept or reject the move now with this probability. So let's look at this. So again, the change in energy occurs. That hopefully makes some sense. If I stick a new molecule in the system and it overlaps with an existing molecule, what will happen? The change in energy will be some very large positive number, and this exponential will be essentially 0, and the probability will be 0, and those moves will be rejected because they're not physically realistic configurations, have molecules overlapping with each other. But if this energy is more favorable, those moves are more likely to be accepted. What else do we see? Well, we have the temperature, and then we have the fugacity here. And again, this hopefully makes some sense that whether we accept or reject insertion moves should be connected to the fugacity. Higher fugacity basically gives you a higher driving force to put more molecules in the system. So it will increase the probability of accepting insertions. The current number of particles in the system also shows up here, n. And again, you can sort of think through whether it's logical that that would be in the denominator versus the numerator. So that's the probability of accepting an insertion. What about a deletion? So for a deletion, we pick one of the existing molecules at random, attempt to take it out of the system, again, calculate the change in energy that would occur, and accept or reject the move with the probability shown here, where again, the fugacity and the temperature and these other factors show up. So we do this millions of times for a given fugacity. So to get an isotherm, what are we going to do? We're going to pick the gas phase, the temperature, obviously for an isotherm, the temperature is fixed. We'll pick, say, the gas phase pressure. Then we'll use an equation of state for the fluid to calculate the fugacity or chemical potential, and we'll feed that into the simulation. And what we will want to calculate is the average number of molecules in the system. So for a given pressure, so we're going to fix pressure, we'll calculate the number of molecules in the system over these millions of configurations, and that will give us a single point on the isotherm. So to get the whole isotherm, we would do a series of these GCMC simulations at different pressures or fugacities and calculate the number of molecules in the adsorbed phase. A few words about codes. So of course you can write your own code to do this. And when I was a graduate student many years ago, that was really the only option. But now there are a number of very nice codes out there that do this and are a nice place to get started. So one code is called LAMPS. This is mainly an MD code. If you're going to do MD, this is a great place to start. But it also does Grand Canonical Monte Carlo. Cassandra is another open source code. This one's primarily a Monte Carlo code. This was developed in the group of Ed McGinn at the University of Notre Dame. And it does Monte Carlo in various ensembles, including the Grand Canonical ensemble. And then there are two codes associated with my group. These are a little more specifically geared toward adsorption. So we have this older music code written in Fortran 90, released back in 2003. And then there's a newer code developed by David Dubbeldam called RASPA. This one's written in C. Both of these are freely publicly available. And the RASPA code in particular has a very nice, nice documentation. Okay, so let's look at some results. So, well, yeah, we already saw this. We can get isotherms for simple things like hydrogen. One complication I should point out, simulation gives us what's referred to as the absolute adsorption, the actual number of molecules per unit volume of the material. Those of you who are expert in the adsorption field will know that experiments give you what's called the excess adsorption. And I'm not going to go into the details, but I'm just pointing out that there's this difference. And if you're going to compare simulation with experiment, you need to convert either the experimental data or the simulated data between excess and absolute adsorption. So I'll end with an example. This is some work we did a number of years ago by my graduate student, Shaji Chempath, and he was doing the simulations. And we collaborated with experimental group of Yuri Denier and Gino Barron and their colleagues. And we were looking at liquid phase adsorption of linear alkanes in the zeolite known as silicolite. Why were we looking at this? Well, liquid phase adsorption is important in a number of industrial contexts. So for example, the Sorbex process for paraxylene separation is done in liquid phase. Certain processes using zeolite membranes for separations would be done in liquid phase. And at the time we started this, most molecular simulation of adsorption really focused on gas phase adsorption. And we wanted to take a look at liquid phase. In principle, the simulations are the same. You still just input the chemical potential into your GCMC simulation, but now the external fluid phase is a liquid instead of a gas. But in practice, under liquid phase conditions, the pores are often very full of molecules. And this means that these insertion moves in the Grand Canonical Monte Carlo become difficult. Why is that? Well, if you think about a pore full of molecules, if you want to do an insertion move, you're going to pick a random location and try to put a new molecule. If the pores are already full, it's very unlikely that these moves will be accepted. And so these simulations become very sluggish. You have to simulate a very long time to get changes to occur. So yeah, what was the problem we were looking at? So these were the experiments. These were batch adsorption measurements. And I'm oversimplifying how they're done, but basically they have their zeolite in this liquid. So that, well, let's start with the zeolite. They have the zeolite there. They add liquid of a known composition. They seal it off, they let it come to equilibrium, and then they measure the final concentration of the fluid phase. And then from a mass balance, they can deduce what actually goes into the zeolite. And the system they looked at was small amounts of n-Alkanes in isooctane, and the isooctane is a non-adsorbing solvent. So our task was, given the temperature and the mole fractions in the liquid at equilibrium, we wanted to calculate the composition inside the zeolite crystals under these liquid phase conditions. And in particular, we were interested in a couple of questions. So this is the zeolite silicalite. This is a representation. It has these straight channels that go in this direction. So here in white would be a straight channel segment. And then in this direction, there are these zigzag or sinusoidal channels shown in green. And those two types of channels meet then in these channel intersections, which are colored in blue. And one thing we were interested in was, well, how many CH2 or CH3 groups can pack into this pore structure for a given chain length under liquid phase conditions? We were interested in how long chain molecules might pack to fill this space, and we wanted to think about selectivity and understand what governs the selectivity for mixture adsorption. So we needed a model. So here's the model we used. In this case, we were lucky because the group of Bernd Schmidt, and in particular Thijs Vloekt, had developed this model already. So this force field they had shown worked very well for single component gas phase adsorption of alkanes in silicalite. And we then decided to see, well, let's see if we can use this for liquid phase adsorption of mixtures. One thing I should point out, this is what's called a united atom model. And that's a bit of jargon that means that instead of having explicit carbons and hydrogen atoms, this model assumes that each CH2 or CH3 group is a single Leonard-Jones site. So a butane molecule would have 4 of these sites. Well, yeah, sort of like shown here. So they had parameterized this model, and you can see that it includes bond angle bending, torsion, and Leonard-Jones interactions. So again, we were given the composition of the liquid phase. Our strategy was a little bit indirect. So to calculate the fugacities, we used the Peng-Robinson equation of state on the liquid and calculated the partial pressures in the gas phase. And since the gas phase total pressure is only 1 atmosphere, those partial pressures are essentially equal to the fugacities. And those fugacities then we fed into the Monte Carlo simulation. So we simulate the zeolite phase and try to predict what goes in here given the liquid outside. Again, we're doing grand canonical Monte Carlo. And I already mentioned the problem at high loading. Let's think again about these insertions. This is a zeolite with these very narrow channels. And we want to simulate, say, hexadecane or some long chain molecule. If we randomly insert a C10 molecule into this zeolite, what's likely to happen? Well, it's very likely to overlap with the framework or other existing molecules in the system. And so when we go to check whether those moves are accepted or rejected, they'll mostly be rejected. So this is a problem. Well, it turns out there's a nice solution to this that other people had developed already. So this is called configuration-bias Monte Carlo. So instead of doing an insertion move randomly, we're going to bias the move. So for example, basically here, we're going to grow the molecule bead by bead. So we'll place the first CH3 group of an alkane at some random location. Well, actually, we might bias that as well. But let's say we put it there. Now we want to place the next bead. Well, we have a fixed bond length. So the next bead is going to go somewhere on the surface of a sphere around the first bead. So we'll try a number of different possibilities, maybe 10 or 15 different possibilities. We'll calculate the energy of each of those, and then preferentially, we'll pick one that has a low energy. Not necessarily the lowest energy, but there's some probability to pick low energy possibilities. So now we have 2 beads placed. Where do we put the third one? Well, if we have a fixed bond length and essentially fixed bond angle, it's going to be somewhere here on the surface of a cone. So again, we'll try a number of different possibilities. And again, pick one of the low energy ones preferentially, maybe that one. And we just keep going. We place the next bead, and we keep going until we've grown the whole molecule. Now, since we've biased the move, we have to adjust the acceptance probability, and I won't go into the details of how that works, but the textbook by Frankel and Smith is a great place to learn more about that if you're interested in the details. So by doing this, we can basically thread these long chain molecules through these very narrow pores. And so, yeah, I have a few minutes. I'll show you a few results. So these were some experimental results from the group in Brussels. They had measured the saturation loading of single component linear alkanes from C5 to C22. And plotted as the black bars, we have the number of molecules per unit cell. And you can see it starts up here around 7, drops to 6.5, and then there's a very drastic drop at C8, and then it's sort of level for a while and gradually goes down. You could also plot this as the number of carbon atoms or methyl groups per unit cell. That's in the white symbols, and that starts here around this axis now. So it starts here around 35, it goes up, and then there's this drop again at C8, and it gradually goes up until it plateaus out. So for these longer chains, there's essentially a maximum number of CH2 or CH3 groups that will fit in the channels of the zeolite. So we wanted to see, could we understand this? Could we explain, for example, why there's this big drop here from C7 to C8? So here are the results. I'm sorry that it's a table, but these are the experiments from the previous slide, the saturation capacity. And this is what we got from simulation. So first we can see there's good agreement. We predict this rise from C5 up to C6 or C7, and then a drop at C8, and then again a gradual rise. But why do we see this? Well, we can start looking at the molecules in the channels. And what we see, and some of this was known before, but not specifically for liquids, for hexane, a hexane molecule just fits in these channels really nicely. And so you can more or less fill the pore space by putting a hexane molecule in every straight or zigzag channel. If you get up to C8, to octane, it's just a little bit too long. And so if it's sitting here in this channel, it sticks its head into the intersection and maybe even a little bit into the next channel. And so you end up basically blocking certain parts of the system. However, as you get to longer chains, they do some things that C8 doesn't do. So for C8, we rarely saw it bend very much. But C14, we see that it can bend. And so it fills the pore space very efficiently. And we also saw something a little unexpected. At a given channel intersection, 2 of these C14 molecules can actually cross. So both of them are passing through a given channel intersection here. And so this combination of bending and crossing at the intersections allows you to really fill up the pore space with these longer chains. Yeah, so it gives us some insight into what's going on here in these experimental results. We also then looked at mixtures. So again, in the experiment, they're varying the mole fraction, say, of C5 in the liquid, here in a mixture of C5 and C6. So as they increase the amount of C5 in the liquid, the number of C5 molecules in the zeolite goes up, and the number of C6 molecules in the zeolite goes down. And that's, of course, what you would expect, that qualitative trend. They can actually measure the number in the zeolite. And the simulations are the open symbols, the experiments are the filled symbols. And you can see there's nearly quantitative agreement here for this system. And then we can also look at other mixtures. So here's C6 with C8, C6 with C10. And now the shapes are rather different depending on the chain lengths of the 2 species. But again, we reproduce this very nicely. Same thing here. This is now C8 with C9 and C8 with C12. So these very different shapes. And again, this was a model developed by Flucht for single component alkanes. And what we see is that if the model worked well for the single component systems, it's giving us nearly quantitative agreement for the mixture behavior. And then, yeah, we can look at where the molecules sit. So here, for example, in this mixture of C5 and C7, the shorter C5 molecules in green prefer the zigzag channels, and the slightly longer heptane molecules in blue, they prefer the straight channels. And in general, both molecules would like to go into the straight channels if they could. So the heptane sort of wins that competition and forces the pentane molecules into the slightly less favorable zigzag channels. So the conclusions from this, this example, we saw that modeling of liquid phase adsorption is feasible with Monte Carlo simulation using some pretty sophisticated simulation methods. In particular here, this configurational bias Monte Carlo. And that was really essential to doing this work. And we also saw that if a force field works well for single component adsorption, it should predict the multi-component behavior, I would say nearly quantitatively. And if you're interested, the references for this work are given here. So to wrap up, I'll just show you this slide again. What did we talk about today? We talked about how to calculate isotherms, and we talked about what would go into a model for a system like this. That model then is used in grand canonical Monte Carlo simulations. We talked through the basics of how those simulations work, and then we looked a little bit at some of the sorts of things that you can calculate from such a simulation. So I'd like to end by just saying that I hope all of you scattered around the world are staying safe and healthy. I would be happy to take questions, and I'll leave this slide up with some references. At the top, these are general references about molecular simulation of any sort of system. And then at the bottom are a few review articles from my group on molecular simulation of adsorption. So yeah, I will stop there and see if there are any questions.
Oh, thanks, Randy. We have one question from YouTube. This is from William Smith. How do you calculate the pressure in the adsorbed phase?
So in the work that I showed you, we basically don't. So we're fixing the volume of the system. And since the volume is fixed, in some sense, it doesn't make sense to talk about a pressure. Now, in other cases, people let the volume fluctuate. And then it makes sense to think about calculating a pressure. And the way it's done is basically, there's these very complicated formulas, but they sort of boil down to thinking about a box around your system and calculating the forces that are exerted on the box around your system. So going back to sort of a mechanical definition of pressure, what is pressure? It's force per unit area. So you can think about the force exerted on the I don't want to say walls, because walls has a different connotation in adsorption, but basically the force exerted on the imaginary box around your system.
Thanks, Randy. While I'm waiting for other questions, I have one myself. How do you treat the mixtures? For example, when we look at the mixtures experimentally, we often try the IAS, and if it doesn't work, we start looking at activity coefficient kind of models. When you don't have experiments, how do you approach this problem from a molecular simulations perspective?
Well, if you have a good equation of state for the vapor-liquid equilibria, or good thermodynamic model for the vapor-liquid equilibria, you can use that to calculate the fugacities of each individual component, and you feed those into the simulation. And so the simulation just then uses those as input, and you don't need to make any assumption like in ideal adsorbed solution theory about what's going on inside. you can really calculate what's going on. So for example, the stuff I showed you with the liquid phase adsorption of the alkanes, there's no assumption of ideality there. Now, if you don't have a good model for the fluid phase, then you might want to do Gibbs Monte Carlo, where you explicitly model both the adsorbed phase and the external fluid phase.
But would you make any assumptions about interactions on the surface?
It all goes back to your force field. So yeah, maybe I left a piece out of the force field. So often what you have in the force field are, say, Lennard-Jones parameters for the framework and Lennard-Jones parameters for the fluid molecules. Now you need to think about how they interact with each other. And usually people use these so-called mixing rules, sort of averages of a particular way of averaging, say, the epsilon and sigma from the two atoms that are interacting with each other. But yeah, the simulation includes all of the interactions between all of the atoms. The green molecules interact with the blue molecules, and the green and the blue molecules both interact with the framework. All of those interactions are included as part of the force field. They're part of the energy. At every configuration, you're calculating the total energy of the system. All of those interactions go into that energy. And the question is how to get the parameters, but yeah, the basic idea that all of those interactions go into the energy, that is something that I should stress.
Excellent. I have 3 more questions here. This comes from Marcus De Mello from YouTube. How can you explain the preference of silicalite for C7 over C5? Is there?
So in general, the longer chains will be preferred enthalpically. Sometimes the smaller species might be preferred from entropic reasons. So the fact that the C7 is preferred over C5, I guess I can go back and look. Where was it? Oh, well, I guess here we don't. Well, here, yeah, you can see that the C7 is preferred. There are more blue molecules. I think it's mainly enthalpic. It's an enthalpic driving force that the longer chains are just preferred enthalpically, and in the mixture they sort of win out. Now, of course, the total configuration or the total loadings here will depend also on the loading in the fluid phase, as you can see in these diagrams as well.
Okay, excellent. So I have another question. This comes from Guoping Hu from here on Zoom. For longer carbon chains, the graph showed that the intersection cross between the two molecules. So how is a C14-C14 interaction considered?
It's just through these Lennard-Jones interactions. So, well, this is not a very detailed picture, but if each of these is a methyl group, methyl or methylene group, all of those have each of those CH2 or CH3 sites has a Lennard-Jones site on it. And so that would be true on, this C14 molecule that's going horizontally and this one that's going vertically. And so what that means is if they get too close, they repel each other. The R to the 12 term in the Lennard-Jones potential reflects repulsion if you get too close. But it means if they get a little bit close to each other, they attract each other through the R to the 6th term of the Lennard-Jones potential. So yeah, you can see here, they want to stay, they don't want to get too close to each other. And then they also have those interactions with the walls. They can't get too close to the walls or they'll get repelled, but they're attracted to the walls at the same time. So there's some balance of those forces here, and the intersection is big enough that these can both fit through there, which maybe wasn't obvious ahead of time.
Yep. So this comes from Huang Tran. Can you infer the absorption free energy from isotherms? And if so, how do these experiments compare with quantum calculations?
You can get free energies. It's, as you might guess, everything with free energy is difficult. It's a little more difficult. I mean, a simple way to do it is if you get the Henry's constant, so the slope of the isotherm at low loading, That's very directly related to the Gibbs free energy of adsorption. And then I think the second part of the question was how this compares with quantum mechanical calculations. There can be some differences. So in quantum mechanical calculations, what you typically do is you find the minimum energy configuration, basically 0 Kelvin. And an advantage of doing these force field models is that you're simulating systems at finite temperature. So you're averaging over multiple configurations that reflect the temperature, rather than just looking at the lowest energy configuration that you would get from a quantum mechanical calculation. But you know, there are a number of systems where people have compared, and the results tend to agree pretty well. It depends, you know, on the force field. It depends on what level of quantum mechanical calculation you're doing. But yeah, that idea of linking those things together, checking that they compare, is certainly something that a lot of people are doing these days.
So I'm going to come to the last 2 questions. So this comes from Marco today. So the approaches described here, do they also take into account chemisorption? And if there is an ideal limit to the strength of interaction between the adsorbate and the surface?
In principle, these methods could take that into account. In practice, it boils down to your force field. And the sorts of simple force fields that I described here really do not reflect chemisorption very well. So for example, in MOFs, if you have exposed metal sites, the simple force fields that I described here don't work very well. And so actually it's a case where you might want to use quantum mechanical calculations to understand the binding with that metal site better, and then somehow feed that information into a simulation. I forget what was that. Sorry, go ahead.
But what you're also trying to say is that you could, if you have the right force fields, also take into account chemisorption in a more formal way.
That's correct, yes. Yeah.
So this comes from Nancy Davia. So if there is no information available about the coordinates of the atoms, for example, in a new MOF structure, is there a way to predict it, and can it be validated?
Okay, I'll answer the question specifically about MOFs, since that's what was asked. I mean, if you know what the building blocks are of the MOF are, you could hypothesize structures. I mean, the best way to validate them would be with X-ray diffraction. So some groups have done that. So you make a new MOF, maybe you can't make a big enough crystal to do single crystal X-ray diffraction. So you can't get a structure, but you get a powder pattern. You could then hypothesize different structures from what you know about the building blocks, create those structures on the computer, simulate their powder X-ray diffraction patterns, and then compare them with the experimental powder diffraction pattern. And if they agree, it's not conclusive evidence, but it's pretty strong indication that that's probably what the structure is. If they disagree, obviously, then it's not the right structure. So that's one possible way to address that.
Sorry, this probably is the absolute last question. So this comes from Mohammed bin Yamin. How does the simulation differentiate between adsorption and interaction among molecules? Is there a cutoff that you need to specify?
So there is a cutoff, but it's not maybe exactly related to what's being asked. So the cutoff that we use when we calculate these Lennard-Jones interactions, we don't do them out to infinity. We usually do them out to, say, a cutoff of maybe 12, 15 angstroms, because beyond that, the interactions are basically 0. But in terms of the question that was being asked, all of the atoms interact with each other if they're within, say, 12 or 15 angstroms. All of the atoms interact, whether they're in the framework or in the guest molecules. So in calculating the total energy of the system, we don't really have to discriminate in that way between them. Now, on the other hand, we can extract out guest-guest interactions versus guest-host, and that's actually really useful to look at that. to see how the energy breaks down into guest versus guest host.
Excellent. Thanks, Randy. That kind of brings us to the end of the questions. I'll turn the microphone to Dan.
Thank you, Randy, for your outstanding webinar on molecular simulation of adsorption. We also thank all of our attendees for joining this webinar and hope that it was both educational and enjoyable. Please join us again tomorrow at 10 a.m. New York time for a webinar on high pressure adsorption presented by Dr. Ronnie Pinney from Imperial College London. I hope you can join us. Additional webinars will be held next week. The first two will be by Professor Stefano Brandani and Enzo Mangano from University of Edinburgh on May 5th, and then from Philip Llewellyn from AMU in France on May 7th. Join us for future webinars, and please follow updates on our website and on Twitter. With that, please stay healthy, and we hope to see you again soon.